once again on my channel. Today is a Friday night, and I took an early nap, which means that it's about 2 a.m. and I can't really sleep. So I thought, what is more relaxing than reading a bit in my database internals book? This is a book that I purchased. Well, actually, my work purchased it for me. Because for a problem we had, a thing we needed to do, I needed to know about the internals of databases. Which meant that I had to do some research, and this book is probably quite literally the first thing that popped up on Amazon, and it's an O'Reilly book, which means that it's usually pretty good. So I just got this one. It's Database Internals by Alex Petrov, a deep dive into how distributed data systems work. And so I read most of this book, and I say most because I definitely didn't read all of it, but I read most of it in a couple days. I was already really familiar with, well, I wouldn't probably not say really familiar, but I was already fairly familiar with Postgres. I had some knowledge of how MongoDB and Redis and like key value stores, how they work. But I just wanted a little bit more of a detailed knowledge of how they actually store stuff, right? You're like, okay, well, I insert some stuff in a Postgres table, and then using some SQL I can get it out. No, I wanted to really know how the individual bits were stored, and how they were queried and stuff like that. Anyway, I'm rambling on. But I thought it would be cool, like in my other videos, to sort of read through a chapter or a little bit of a chapter. And in my case, I was going to read a little bit in this book from chapter 1, and it's called Introduction Overview, which is, I guess, is fairly reasonable. Oh, actually, there's a part before it. So chapter 1 is on page 7. There's a part 1 that says storage engines, and I think this is probably the real start of the book. So we'll start there and we'll see how far we get. The primary job of any database management system is reliability, storing data, and making it available for users. We use databases as a primary resource of data, helping us to share it between different parts of our applications. Instead of finding a way to store and retrieve information and inventing a new way to organize data every time we create an app, we use databases. This way we can concentrate on application logic instead of infrastructure. Since the term Database Management System, or DBMS, is quite bulky, throughout this book we use more compact terms, database system and database, to refer to the same concept. Databases are modular systems and consist of multiple parts: a transport layer, accepting requests, a query processor, determining the most efficient way to run queries, an execution engine, carrying out the operations, and a storage engine. See DBMS architecture on page 8. The storage engine, or database engine, is a software component of a database management system responsible for storing, retrieving, and managing data in memory and on disk, designed to capture a persistent, long-term memory of each node. While databases can respond to complex queries, storage engines look at the data more granularly and offer a simple data manipulation API, allowing users to create, update, delete, and retrieve records. One way to look at this is that database management systems are applications built on top of storage engines, offering a schema, a query language, indexing, transactions, and many other useful features. For flexibility, both keys and values can be arbitrary sequences of bytes with no prescribed form. Their sorting and representation semantics are defined in higher-level subsystems. For example, you can use int32 or a 32-bit integer as a key in one of the tables and ASCII in the other. From the storage engine's perspective, both keys are just serialized entries. Storage engines such as BerkeleyDB, LevelDB, and its descendants, RocksDB, LMDB, and its descendants, libmdbx, Sophia, HaloDB, and many others were developed independently from the database management systems they're now embedded into. Using pluggable storage engines has enabled the database developers to bootstrap database systems using existing storage engines and concentrate on the other subsystems. At the same time, clear separation between database system components opens up an opportunity to switch between different engines, potentially better suited for particular use cases. For example, MySQL, a popular database management system, has several storage engines, including InnoDB, MyISAM, and RocksDB. MongoDB allows switching between WiredTiger and in-memory and the now depreciated MMAP v1 storage engines. Your choice of database system may have long-term consequences. If there's a chance that a database is not a good fit because of performance problems, consistency issues, or operational challenges, it is better to find out about them earlier in the development cycle, since it can be non-trivial to migrate to a different system. In some cases, it may require substantial changes in the application code. Every database system has strengths and weaknesses. To reduce the risk of an expensive migration, you can invest some time before you decide on a specific database to build confidence in its ability to meet your application's needs. Trying to compare databases based on their components, e.g. which storage engine they use, how the data is shared, replicated, and distributed, their rank, and arbitrary popular values assigned by consultancy agencies such as ThoughtWorks, or database comparison websites such as DB-Engines, db-engines.com, or database of databases, dbdb.io, or implementation language, C++, Java, Go, etc., can lead to invalid and premature conclusions. These methods can be used only for a high-level comparison and can be as coarse as choosing between HBase and SQLite. So even a superficial understanding of how each database works and what's inside it can help you land a more weighted conclusion. Every comparison should start by clearly defining the goal, because even the slightest bias may completely invalidate the entire investigation. If you're searching for a database that would be a good fit for workloads, or for the workloads you have or are planning to facilitate, the best thing you can do is to simulate these workloads against different database systems, measure the performance metrics that are important to you, and compare results. Some issues, especially when it comes to performance and scalability, start showing only after some time, or as the capacity grows. To detect potential problems, it is best to have long-running tests in an environment that simulates real-world production setup as closely as possible. Simulating real-world workloads not only helps you understand how the database performs, but also helps you learn how to operate, debug, and find out how friendly and helpful its community is. Database choice is always a combination of these factors, and performance often turns out to not be the most important aspect. It's usually much better to use a database that slowly saves the data than one that quickly loses it. To compare databases, it's helpful to understand the use case in great detail and define the current and anticipated variables, such as schema and record sizes, number of clients, types of queries and access patterns, rates of read and write queries, expected changes in any of these variables. Knowing these variables can help to answer the following questions. does the database support the required queries? Is the database able to handle the amount of data we're planning to store? How many read and write operations can a single node handle? How many nodes should the system have? How do we expand the cluster given the expected growth rate? What is the maintenance process? Having these questions answered, you can construct a test cluster and simulate your workloads. Most databases already have stress tools that can be used to reconstruct your specific use cases. If there's no standard stress tool to generate realistic randomized workloads in the database ecosystem, it might be a red flag. If something prevents you from using default tools, you can try one of the existing general purpose tools or implement one from scratch. If the tests show positive results, it may be helpful to familiarize yourself with the database code. Looking at the code is often helpful. It is often useful to first understand parts of the database, how to find the code for different components, and then navigate through those. Having even a rough idea about the database code base helps you better understand the log records it produces, its configuration parameters, and helps you find issues in the application that uses it, and even in the database code itself. It'd be great if we could use databases as black boxes and never have to look inside them, but the practice shows that sooner or later a bug, an outage, or performance regression or some other problem pops up, and it's better to be prepared for it. If you know and understand database internals, you can reduce business risks and improve chances for a quick recovery. That is true. I was going to say something about the last part. Is they're like, oh, well, try to read the database code, which I guess if you're using something like, I don't know if there's any database written in Golang. For some reason I was going to say CockroachDB, but like I could probably realistically look at CockroachDB code and sort of understand it a little bit, but to do that with something like Postgres, where it's all in like C, it's incredibly difficult. Like almost like impossible unless you're already really good at C. Looking at the Postgres source code and trying to fix or improve things is like such a daunting task, but I'm sure they don't necessarily or only mean Postgres, so we'll let it slide. One of the popular tools used for benchmarking, performance evaluation, and comparison is Yahoo Cloud Serving Benchmark. YCSB offers a framework and a common set of workloads that can be applied to different data stores. Just like anything generic, this tool should be used with caution, since it's easy to make wrong conclusions. To make a fair comparison and make an educated decision, it is necessary to invest enough time to understand the real-world conditions under which the database has to perform and tailor benchmarks accordingly. This doesn't mean that benchmarks can be used only to compare databases. Benchmarks can be useful to define and test details of the service level agreements. Understanding system requirements, capacity planning, and more. The more knowledge you have about the database before using it, the more time you'll save when running it in production. Choosing a database is a long-term decision, and it's best to keep track of newly released versions, understand what exactly has changed and why, and have an upgrade strategy. New releases usually contain improvements and fixes for bugs and security issues, but may introduce new bugs, performance regressions, or unexpected behavior. So testing new versions before rolling them out is also critical. Checking how database implementers were handling upgrades previously might give you a good idea about what to expect in the future. Past smooth upgrades do not guarantee that future ones will be as smooth, but complicated upgrades in the past might be a sign that the future ones won't be easy either. Understanding trade-offs. As users, we can see how databases behave under different conditions, but when working on databases, we have to make choices Designing a storage engine is definitely more complicated than just implementing a textbook data structure. There are many details and edge cases that are hard to get right from the start. We need to design the physical data layout and organize pointers, decide on the serialization format, understand how data is going to be the garbage collected, how the storage engine fits into the semantics of the database system as a whole, figure out how to make it work in a concurrent environment, and finally, make sure we never lose any data under any circumstances. Not only there are many things to decide upon, but most of these decisions involve trade-offs. For example, if we save records in the order they were inserted into the database, we can store them quicker, but if we retrieve them in their lexicographical order, we have to resort them before returning results to a client. As you can see throughout this book, there are many different approaches to storage engine design, and every implementation has its own upsides and downsides. When looking at different storage engines, we discuss their benefits and shortcomings. If there was an absolutely optimal storage engine for every conceivable use case, everyone would just use it. But since it doesn't exist, we need to choose wisely based on the workloads and use cases we're trying to facilitate. There are many storage engines using all sorts of data structures implemented in different languages, ranging from low-level ones such as C to high-level ones such as Java. All storage engines face the same challenges and constraints. To draw a parallel with city planning, it is possible to build a city for a specific population and choose to build up or build out. In both cases, the same number of people will fit into the city, but these approaches lead to radically different lifestyles. When building the city up, people live in apartments, and population density is likely to lead to more traffic in a smaller area. In a more spread out city, people are more likely to live in houses, but commuting will require covering larger distances. Similarly, design decisions made by storage engine developers make them better suited for different things. Some are optimized for low read or write latency, some to maximize density, the amount of data stored per node, and some concentrate on operational simplicity. You can find complete algorithms that can be used for the implementation and other additional references in the chapter summaries. Reading this book should make you well equipped to work productively with these sources, and give you a solid understanding of the existing alternatives to concepts described here. Well, that's pretty cool. I think we're already like 18 minutes in, and we've just reached chapter 1. I think we'll do this for next time, actually. It'd be cool if we make this like a little series, and learn a little bit more about databases. I think the next chapter is about different kinds of databases and different use cases, and maybe like a little bit about the architecture. So I'm sure that'll be interesting. I hope you enjoyed this video, and I hope you learned something new about databases. And I'll probably see you another time on my channel. Thank you.